So this is something that I only got into a couple of weeks now, like 2 weeks ago, when I had to prepare this talk. So feel free to correct me if anything I say is incorrect or incomplete. So we start very basic from the definition of a Banach ring. So this is a pair of a ring and a norm. Such that, so this is a ring, such that, first of all, the norm of, so I'll always write F for a ring element, right? Because we tend to think of them as functions. So this is the norm of something is 0 if and only if the element is 0. 2, you have this triangle inequality. And 3, you have this, it's multiplicative, semi-multiplicative. So it's not an equality in general. Or sub-multiplicative, I guess it's called, not semi. And 4, R is complete with respect to the topology induced by this norm. Right, so if you have a norm, you get topology, some metric topology where you have this becomes a metric space. And then you get this notion of Cauchy sequences and convergence. And you say R is complete if it's the pair is complete if R is S with this topology is complete with respect to this norm. Okay, so examples. Any ring R with a trivial absolute value. Okay, because here the Cauchy sequence is eventually constant, so of course it's complete, and all the other properties are obvious. You have real numbers with the usual absolute value, which is also denoted with this infinity, and you can raise it to the power epsilon with 0 less than or equal to epsilon less than to 1. Oh, well, no, so this is less than or like this, okay? And so there are many more examples, so I will give another one. So you have, of course, the p-adic numbers with the norm induced from their definition, essentially, as the completion of Q. So on Q, you have this norm P, which makes it this is not complete. You complete it, you get p-adic numbers, and they have an induced norm. I don't know, the list goes on. But for us, the most important example, actually, well, I don't need this. The most important example is, I'll put this here. We start from a Banach ring, and we consider for some R positive, the ring R of convergent power series, of power series on a ring that that converge on a disk of radius R. So this is di such that all the i's are in R, and I have to move this. And the norm of f, which is by definition equal to the norm, you take the norm of the coefficients times r to the power I. This has to be less than infinity, so this has to be some finite value. Okay, so the idea is that if you plug in an element of r into such a function f, and if the norm of r is less than or equal to r itself, so okay, there are two r's. Okay, wait, let me write it down. If r in r, wait, no, there are even more r's. If x in r, such that the norm of x, so this is the norm on r. Let me distinguish them. This is the norm, let's call this norm p, I don't know, power series. And this is the norm on r. If this is less than or equal to r, then for f in fx makes sense. Okay. So this is an important thing, and this is the what I think people call the closed unit disk in the over the ring R. I have to do a new page.
I'm sorry. What does P stand for in the norm of F? Norm.
So there are two things with the same symbol, right? So I just put the P there, but I don't know. It's bad notation.
Okay.
Oh wait. Forget about the P. I just made it up on the spot. But I just want to do something to distinguish the norm on the ring R from this norm.
Okay.
Okay.
Yeah.
Okay. So now what we want to restrict to is, so this is the definition. We want to restrict to non-Archimedean fields. So this is just a pair of a field with a norm. Okay, a field. At this thing. It's a norm such that this, sorry for my unorganized way of writing, is a Banach ring. And the absolute value is non-Archimedean. Okay. So remember, this means that i.e. Okay. So there are some standard facts about this kind of thing. For example, here, equality holds if the norm of F is not equal to the norm of G. So this is not part of the definition, but this is something you can prove. Okay, so this is, we will consider actually in the sequel we will focus on things of the form k r minus 1 t, where this is a non-Archimedean field. And actually, we'll focus on the case R as well. Okay, so this will be the closed unit disk over a non-Archimedean field. Okay. So now, the thing we need to remark though is that if we just work with this definition, so now I'll just write this. So here there's really an R is 1, right? But I will not write it. This is not nice enough, let's say. So you need to do something technical, which is uniformize. So sometimes the pen doesn't register things the way I want it to. If you do this, so this is some general procedure that you can do when you have, I think you can do it for any Banach ring. You get sort of another ring with another norm, and it satisfies some universal property. And in our case, this leads to something which is denoted like this. And this is actually the set. Also a formal power series, AI, TI, such that AI and K. But now the norm is changed a little bit. No, the definition is changed a little bit. Namely, you just require that in the limit, this thing goes to, that this limit is 0. And the norm for an F in there is now by definition the maximum of all I of, sorry, here there's a 1. This is a 1. Sorry, I don't know where the eraser is. So this is a 1. So here usually there's an R, right? But here we have put a 1. So the R there is not there. So here this is now just the maximum of the norm of the coefficients. Okay. So this is sort of a canonical, you get this ring out of this ring by doing a canonical sort of procedure. And this ring is for some reason nicer. So we'll actually focus on this ring. Okay, is that clear so far?
So what was the ring with angle brackets? What was the difference?
In angle brackets, wait. You also have formal power series, but the definition is different. So here you have the sum has to be finite, while here this limit has to be 0. Sorry, here there's an absolute value. Right, which is not the same. And also the norm is different, right? So here you just take the maximum absolute value. Oh, wait. This zoom thing keeps popping up and then I cannot click back. Here the norm is you take the sum of all the absolute values. And here we just take the maximum.
Okay.
Okay, so this is something else. Okay, so important thing then is Gauss's lemma. So 2 S's, I guess. That this norm is multiplicative. Okay, so i.e. norm of f times g is equal to the norm of f times the norm of g. Right, so usually in the definition of a Banach algebra, you only have this thing. But so now you also have this thing. Okay, so we'll need one more, we'll actually now introduce the, so this, so out of, let me just recap, we have K like this, non-archimedean field. Out of that, we get K D, and out of that, we get K. Okay. So this is sort of supposed to be like polynomial ring. Well, not quite. Actually, I guess that's not completely said. But this is, anyway, it's a ring. Let's just say it this way. So in algebraic geometry, right, out of a ring, you want to get the space. Right? So usually you would take the spectrum, well, I guess out of an algebra. But here you don't need to, so here you don't take the spectrum because there is more information around than just the ring, right? We also have the norm. So there is actually sort of a valued version of the spectrum. That's what we will define now. So it's the Berkovich. Spectrum of combined. So this is, you know, that MR, which is the set of multiplicative seminorms. Such that the norm of the element 1 is 1, and the norm of any f is less than equal to the norm of the of f under the, so that is this one, under the given norm on R for all. Okay. So this is, right, if you do a spectrum, you would take prime ideals, but here you take multiplicative seminorms. Okay, so our goal for the first part of the talk is to describe M of this closed unit disk algebra. Okay, so this is the closed unit disk. So this is our goal. Okay, so we already saw, okay, so we will describe the points, right? So our goal. Understand and okay, and so I forgot to say, of course, this is not just a set, but it is actually a it has a topology as well, and I guess also a structure sheaf, and there's a whole story there, but that we don't need any of that for this talk. It's quite complicated, I think. So we will only think about, well, we do want to think about a little bit of the topology, but not too much. So we just want to get a sort of intuitive understanding of what this is supposed to be. So we already saw by Gauss's by the lemma of Gauss that this norm, right, which is max the absolute values, lies in the in here. Right, and so the content in this statement is that, of course, this is the norm. This is the norm. Right. So if we go back, can you see my mouse pointer, by the way?
Yes, we do.
Okay. So of course, these two conditions are both satisfied for the norm on R. But there's an extra condition here is that we only work with multiplicative seminorms. While in the definition of this Banach algebra, it was not required that the norm on R is multiplicative. Right, so the content when you say that this that the norm on R lies in the Berkovich spectrum is that the norm on R is actually itself multiplicative. And so of course this is then also the maximum element by definition. Right, for all other norms. Okay, by the way, I will now just write no. They're all smaller by the evaluation than this given norm. Right, so this is just if you evaluate anything in this thing and in this thing, if you evaluate any element of the ring in both sides, this equality holds. Right, so this is i.e. this thing is maximum. Okay. So we already have 1 point, right? We have, and we will also denote this by xg, which is the Gauss point. We have 1 point already. Okay, now it is important that we now make some assumption. We assume k is non-trivially valued. And for simplicity, we'll also assume that k is algebraically closed. Okay, right. A nice result. If this holds, then any norm on is determined by the values it takes on -a. Okay, so the thing here is, so if we have a norm on this algebra k curly bracket t, then it is completely determined by the values it takes on these linear polynomials. And that's because so this is since the polynomial ring which sits inside of this is dense. And then you just use the fact that it's multiplicative. So any multiplicative. right? So because it's algebraically closed, anything here is a product of things like that. So if you know the value on that by the fact that it's multiplicative, you know the value on any point. And then because this is dense, this determines the norm completely on the whole algebra.
Robin,
Okay.
a question?
So, yeah.
Ask a question. So if it's not algebraically closed, is the norm determined by the value on each irreducible polynomial?
I guess so, yeah, but I'm not sure. It seems that this reasoning should hold. Dimitri, do you want to say something?
Yes, this is the case. So you are going to now to describe this Banach spectrum in case the ground field is algebraically closed, and you can think of the case when the field is not algebraically closed as the quotient of it by the action of the Galois group of the ground field. It's very similar to scheme theory. So in scheme theory, if you change your ground field, you have points identified by the action of the Galois group. So same as here.
Okay, thanks.
I think it's telling me that my internet is unstable. Am I clear? Is the sound okay for you guys?
It's okay, yeah.
Okay, because I hear you very robotic. Okay. Right. So remember, we're going to understand this Banach spectrum. Okay. So we have one point, and we have made this observation. Now we're going to describe more points. So we define some disks. So one is what is called, I think, a rigid disk. So these are elements in, wait, I'll just completely erase this. Elements in the field K such that their norm is less than or equal to R subset of the field. This is called the rigid disk. And there is also another disk, which is okay. Okay, so we have two disks, two types of disks. And now the nice thing is that there is a map. We have a map from this rigid disk to this Berkovich spectrum. And this says you take an element A and you map it to corresponding norm. And this norm is just the thing that maps that maps an element F to the norm of F. Okay, so what you do is you have the element A, and it lies in this unit disk, in this rigid disk. And now we already saw that for points like this that satisfy this condition, you can plug them into elements of this algebra. So you plug them into the algebra, you get an element of the field. On the field, you have your absolute value. So this is the absolute value. The norm just on K. And this is the value that you let the value of the norm on the function f. Okay, so this gives a whole bunch of points, right? One for every element in this disk. Okay, right? So the image.
Sorry, these are semi-norms. These are actually those points for which you need semi-norms and not just norm.
Yeah. So they're semi-norms. So of course here in the this is so annoying. I don't. Oh, wait, I can just move this. Okay. So here we have the Banach spectrum of the Banach ring is just multiplicative semi-norms, so not real norms. So they can take. So this means that they can take zero value on elements other than the zero element of the ring. And of course, this is the case here. Okay, so the image of this map is a set of type 1 points. So this is the definition. Okay. So now, if we now draw a picture, we already have a little bit more. We have the Gauss point, and then here, down here, we have a lot of points all lying in the disk. Great, this one. Okay, but there are more norms. There are more semi-norms. So construction of type 2 and 3 points. This is, you take a disk, E, A, P, which is defined to be X in ER, such that okay, and here A is a point in K, B, okay, so this is sort of a subdisk of ER, where you take a center A and a radius P, right? So I think you can think of this as you have here, you have your ER, here you have your point A, you have a smaller disk with radius P inside of it. Okay. Now out of something like this, you can get a new semi-norm. We define the norm of F that we obtain from this disk. So by definition, the maximum over this, where the expand F is a power series around the point A. Right, so we can take a power series expansion of the function F around the point A. We get coefficients, and then you take this maximum. Right, so essentially this is, right, if the original norm corresponds to taking the maximum value on the whole disk, now here you have the subdisk, and essentially what this is saying is you send F to the maximum value that F attains on this subdisk. This is essentially the idea. Right, so this can also be described as the supremum over points B inside this A, closed the absolute value of B, where right? So this is essentially what I said before. So this is one definition, but you can equivalently describe this norm as you plug in all values that lie inside of this, that lie within a range P from the point A. You evaluate F in these points, you take the maximum of the absolute values that you can get in that way. Okay. So all of these are also semi-norms. Now here's an important remark. If A and B, elements of the field, are such that the absolute, or the distance between them is less than or equal to P, then the corresponding disks they define with radius P are equal. So this is something typical of the non-Archimedean world. And also the norms, of course, then also, I mean, suggested by this notation already, the norms are also different, are also the same. Right, so it's not immediately clear, by the way, that this definition here, the subscript here is this disk, but it's not so clear that this only depends on the disk, right? Because you expand around the point A and you have this P. But really, it turns out that if you have two sets, A, P, and A prime, P prime, such that these things are the same, then also the norms are the same. Okay. Right, so you would, out of this, for every combination of a point A and a number P, you get this semi-norm. But this says that some of them are equal, right? So it's not like these give all different points. Is that clear so far? So we're just constructing more points in this Berkovich spectrum still.
So the value of this semi-norms is also the same as taking a maximum of the function on the disk of, or the disk and the subscript. It doesn't turn out to be the same thing.
It does or it doesn't?
I think it does, yeah.
Okay, okay. So that's sort of similar to this definition, except you take an E here. Yeah, okay. So now the nice thing is that once we fix a point A in this rigid disk of radius 1, so this is a subset of the field, we get a map. I don't know if there's a standard name for this map, but from the unit interval to this, oh wait, yeah, okay. This is the space we're interested in. Which sends the value T to the norm that you get by taking a disk with center A and radius T. Okay, and the nice thing about this map is that if you plug in the value 1, then what you get is always just the norm corresponding to the disk center A radius 1. So that is equal to the norm of the disk with center 0 and radius 1. But this, by definition, is just the norm on him, which was this Gauss point. And at 0, right? All you do is you take just C0 in this notation, right? Because now P here is 0. So all of these contributions for I positive vanish, and you only get the contribution of the zeroth coefficient, which is just the absolute value of F in A, which was just the type 1 point that we already found before. So now we get this sort of interpolation from these type 1 points to this Gauss point along this unit interval. Okay. But remember, right, we saw before that EAT is BT of A minus B. Okay, right, so for using this observation, we can make this drawing now. Right, so here we have our type 1 points. For example, here we have an A and a B. And here we have this Gauss point. And right, out of any point, we have this interval, right? This is the image of this map that we described. And now out of B, we also get this a path from B to the Gauss point. And so here, by the way, these points are regarded as they are identified with the type 1 points that they correspond to. So here we have the right. So we saw out of any point in this closed unit disk, we get this type 1 point that it defines. Right? And so all these paths start from there and they end in the Gauss point. And now here we see, right, the value of this path at any point is the norm with center A and radius T. So this will mean that these two paths, they eventually join. Now I'm starting to think maybe I have this equality the wrong way around. Let me think for a second. Right, so these start out as different points, but for a large enough radius, they coincide. Yes, I think this is the other way around. Yeah, I think it's like that. So the point is, anyway, that we start, so this is the path gamma B, so the path gamma 1. They start this joint. One starts in the point A and the other in B. And for a large enough radius, the two disks coincide. And you get this for every point, right? And some, they only like join all the way up there, etc. Right? And then these will also at some point coincide, etc. So you get this huge tree structure, which has roots corresponding to the rigid points, the type 1 points, leaves, I mean, and a root corresponding to this Gauss point. Is that clear? Yeah. Okay. So one thing that is important also to note is that this the radius function which maps something of this form, A, T maps to T, is well defined. Okay, so you can actually think of this as here there is something that keeps track of a radius. And here the radius is 1, and here the radius is 0. Right? And the point where these two branches meet, the branch that starts at A and the branch that starts at B, here, is exactly here. Oh wait, maybe it was the wrong way around before. Sorry, I'm so confused about this. If T is, yeah, no, sorry, it was the wrong, it was the right way around before. I will try to find an eraser. I cannot find an eraser, sorry. Right, so this is saying that the two disks are equal if the radius is larger than the difference between, than the distance between the 2 points. So these 2 points, right, all the points on this line correspond to these disks, and the disks are equal exactly from the point that the radius equals the distance between the 2 points, right? And so here, if this is a point C, these 2 branches would meet at C minus B, right, etc.
I guess another way to put it is that for any disk, any point inside this disk is its center.
Yeah, this is a result of what you just said. Okay. Okay, so also as a corollary, okay, so this was just a note, but it's important, this is an important function. I will write this as rad, which is the radius function. Okay, and so as a corollary, because it's not really anything special, but we have branching at the point x in E1. So branching means that 2 of these branches come together in the point if the radius of x was in the value group. Which is the image of k under the absolute value of k, which is a subset of x. Okay, right? Because we see that any time 2 branches come together, that only happens when the radius is equal to the distance between the 2 points. And this distance, by definition, only takes values in the value group. Okay, so these branch points are type 2 points and non-branch points type 3 points. And so the distinction is mostly between the radius lies in the value group for that one, and the radius is not one. Okay. Okay, and then there is a subtle point. So at this point we have a better understanding. So here we've got the rigid disk, the Gauss point, and then this whole tree structure. And the subtle point is the type 4 points. So they correspond, so at this point we have type 1, here we have type 2 and 3, and there are more points, and they are type 4 points, and they correspond you have a disk here, and then you take a smaller disk, and 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 you get a decreasing sequence of disks, as far as I understand it, that keeps decreasing, but is never empty. And so the radius keeps, I think the radius keeps decreasing along these chains, but you don't end up with a type 0 point. And this has to do with the existence of these infinitely nested balls inside of your field, I think. But this is subtle and will not worry too much about this. So these points exist like infinitely nested disks.
So if the field has the property that every such infinite collection of nested balls has a point inside it, it's called spherically complete. And if you assume this, then you don't have type 4 points. They're all just type 1 points.
Yeah.
This is often a simplifying assumption.
So I'm not sure about the interplay between being algebraically closed and being spherically complete. I don't know if you know anything about that, Dimitri, but I know I read, for example, that the p-adic numbers apparently, I think, are spherically complete, but algebraic closure is not. So is this a general phenomenon, or?
It's a bit subtle. So spherical completion exists, but it's not. I think in general it's not completion of the algebraic closure.
But it's not that algebraically closed automatically rules out being spherically complete.
No, it doesn't, but it also
okay. So it's just independent things. Okay. So I was just worried that if I want to make two simplifying assumptions, then the algebraically closed and spherically complete, that I end up with nothing. But that's not the case. Okay.
Robin, can I ask a question?
Yeah.
I'm not sure if I missed something or not, but are you using this as definition of type 3 points, or did I miss definition?
Yes. This is a definition.
Okay.
Both of these are actually all four are definitions, essentially. Okay, and so then the claim is this is everything. Okay, so now we kind of understand this this closed unit Berkovich disk. Okay. Yeah. So that was the introduction on that. Maybe it is the exact right time for a short break.
Yeah.
Okay, let's go then. Okay, so now we will talk about, we now sort of understand this object. So this is check. But now what we want to do is do something similar to what we, to this Desmailly approximation that we saw in the complex setting, but now we want to do it on this space. Okay, so first what we need is a definition of, I think it's called quasi-subharmonic function. Okay, so a function. Phi from x. So it can take minus infinity as a value, but not plus. It's okay, so our x, from now on I will always denote x like this. I will always use it to denote this Berkovich spectrum of this closed unit disk. So this is a round bracket. This is called O0 subharmonic. Where this is a Dirac mass at the Gauss point. So essentially this is a measure that only takes a value when you're at the Gauss point. Okay, so it's a measure on the closed unit disk, such that a function is called if one for every finite subtree So the X rig here, this is just a collection of type 1 points. Containing xg, function restricted to the tree is continuous. And the restriction is, so we restrict our function to this finite subtree, and then it's continuous, but it's also convex on every segment. Not containing the Gauss point. And B, and this is the important condition of, well, the other are also important, but this is something. Right, so for every point in this subtree, we have the following relation. We evaluate this Dirac mass at the point. So this is just 0 if this y is not the Gauss point. Plus, and then you take the sum over the tangent vectors at the point. I will define what this is in a moment. And then you take the directional derivative of the function in the direction of this tangent vector. So this is supposed to be greater or equal than 0. And then there's a second condition. So this is 1, 2, technical. I will not. So this is something about the function as a whole being a sort of limit over finite subtrees or something like that. But that's not so very important, I think, for now. Okay, so this is something we saw before in the earlier talks, this sort of expression. So let me just recall, right? If we have this 3, and this is the point y, right? And maybe here there's more branching. Then what you do is you take out the point y and you're left with, in this case, 3 connected components, right? And each of these connected components represents, or is by definition, a tangent vector. So these things are the tangent directions. Right, so it's just a set of connected components of the 3 with the point y removed. Okay, and then if you have one of these tangent components, so for example, if you choose this one, right, if you now just look at this, and so here is the point y. If you take d, so if this is our point v, if we take the directional derivative of something in a direction of v, then this is by definition. Okay, wait. Shouldn't have started this there. This is by definition the limit over the points x in this tangent direction. So that x approaches y of 5x minus. And then here is something ax minus ay, where ax I think this is the correct definition. So this was not explicitly mentioned in the article, but I think this is the standard definition for the derivative. Do you agree, Dimitri, that this is how you should define it?
Yes.
Yeah. Okay, right. So essentially this interval, what they're saying is you just sort of parameterize it, or you take a metric, let's say, which is given by the distance between 2 points is this difference. So it's not, if you have 2 points, the distance is not just the distance in radius, but it's the distance between minus the logarithm of the radius. Right, so it's, you take the derivative with respect to a remetrization, let's say, of the interval by this logarithm. Okay. Okay, so let's give a quick example. So something which should definitely be subharmonic is this thing, which is by definition the function that maps the point x, maps it to log of. Right, so the point x is the semi-norm. So this part here is is an element of him. So we can take this evaluation and we can take the logarithm. So this should be, by analogy, subharmonic function. Okay, right, so let's quickly test this. And first let's describe what this function is actually. Right, so if we have a b in the closed unit disk, and we have some radius, right? So this gives a norm. And remember, all points essentially, besides these type 4 points, all points are essentially of this form, right? So let's think about this expression. Now it's easy to see that this is, okay, right? If you follow the definition, this is the norm. Right, so this is how the norm worked, right? You expand the function around the point B. So that's what we did there. And then you take the maximum of the coefficients that appear. So this is just the maximum of the norm of B minus A. Right, but this is then times t to the power 0. So this you can leave out. That's the maximum between this and 1, which is this coefficient, times t. Right, so this is just the maximum of the distance between A and B and t. Okay, so this is a very simple function actually, right? Because what this means is if we draw a picture, so this is our Gauss point. Here we have our point A, right? We consider the function t minus A. And if here we have another function, another point B, then on this whole segment, the function is constant with value this thing. And on this whole thing, the function of the value is just t, which is this radius, right? So this, maybe I shouldn't even use the t. So it's just the radius function. Right, so you see that essentially, although the tree is very complicated and all that, the only point at which the function takes a non-trivial value, like really changes, is along the path connecting a to the root of the tree. And along any other branch, the value is just constant, equal to the point where the branch branched off of this special branch. Okay, so also here it's constant, etc. And all these parts will be constant. So what that means, right, is that if we have a tangent vector, right, xg, here we have our point A, here we have our point Y, and we have some branches here, right? If we take the tangent vectors, right, so they are this branch, they are this branch, and then there are these other branches. Clearly, along any of these tangent vectors, the derivative is 0. Right? Because the function doesn't change along the branch. It's a constant function. Also this one. So the only place you will have a non-zero derivative is in this tangent direction and this tangent direction. And actually, if you work out, right, the formula here, you will see, for example, that for this one, the definition says that you take the limit, epsilon goes to 0. I'll just write it out once. The logarithm of t0, so t0, the radius of y is t0 plus epsilon minus log of t0. Right, so remember, we take the function log of t minus a, which is log. Oh, okay, so that's why you have the log appearing here, right? So on this branch, the function is just equal to the radius function, which is this t plus epsilon, and then you take the logarithm because we have the logarithm here. So this is the thing above the line. I forgot the name, the numerator. And then here you have the absolute value of minus log t0 plus epsilon plus log t0 absolute value. And if you work this out, this is just 1. And if you do it here, you get minus 1 because you approach from the other direction. So you see that the sum is 0, right? Which is what we wanted. Is this clear? Okay, I guess that means it's clear. So there is another point. So this is if you choose a point y in the middle of the branch, right? But what if y is the point A here? Right now there is only one tangent direction, and that is the one pointing up towards the Gauss point, right? So it's essentially this one, right? The computation will be the same, right? So in the point A, if you work out this sum, right? You have the sum of all tangent directions. And if the point y here is equal to this rigid point, there's only one element in the sum here. If you work at the rigid point, which because there is no branching there, it's only one direction. And you get this value 1, right? Which is greater or equal than 0. So that also works. Then there's one more point, and that is if y is the Gauss point. Yeah. Right now, again, there's only one tangent direction, and that one is similar to this one, right? You approach, there's only one tangent direction, and you have to approach from the top, and all the other ones are 0, right? Because on any other branch, you don't get any changes. So there you get minus 1 as the only contribution, and any other branching all contribute 0 there. So the conclusion is that, that the sum over v in t at the Gauss point of x of dv is minus 1. But of course, we add this Gauss mass, this Dirac mass at the Gauss, which is concentrated at the Gauss point. So we can add something here. So this will be subharmonic if, as long as this mass of the Gauss point is greater or equal than 1. Right, so you see that indeed the logarithm function of a linear form like this is subharmonic if you use the correct mass at the Gauss point. Okay. So the conclusion. Log 15 is subharmonic. And this works also for other kinds of polynomials. The analysis is more complicated, but it's essentially the same, right? You'll again get this constant on most branches, and but it's a little bit more tricky, but it's essentially the same. Okay, so this is just a
show it is to just represent your polynomial as a product of linear factors. For linear factors, we have just shown that it's subharmonic, and then sum of subharmonic. Then you have to show that some subharmonic functions is subharmonic, but I think it's not very difficult. This condition is additive.
It's linear, I think. I think this condition is if you take the derivative of the sum of two things, it should be the sum of the derivatives. So I think you're right. It should be easy. Okay. Okay. So anyway. The point is, so like in the normal, in the classical sort of situation, log of the absolute value of f is a nice subharmonic function. Right. So things of this form are also said to have analytic singularities. Right. So the point is, like what we did before, if you start from an arbitrary subharmonic function to approximate it by something which has analytic singularities. So this is our question. Can we approximate by things of the form beta plus log wait, I guess it was something like that, something like this. Alpha I. And this is bounded. Right, so we start from something arbitrary, which can be complicated potentially. But to be honest, I don't have a very good intuition for what this could look like or how something like this would arise in practice. Right, it arises in this form. I don't know how you get something more general than that. But whatever, let's say you do start from something like that, which you somehow get out of something else. Can you approximate it by things like of this form, which are sort of easier to understand, I guess. And so technically, I think you want this to exist, so this approximation to work. You want the thing by which you approximate this phi to locally look like this. So on what they call a phenoid open domains or something, but I don't know too much about that. So to me, it's just a global sort of statement, but I think that's sort of a detail for us.
I have a question. You want to approximate by things that of the form bounded plus sum or maximum?
I think a sum.
Okay.
But in our case, let me see. Yeah, I think it's a sum.
I actually think that it is a maximum or something similar to it, because well, I mean, just open the paper of Stevenson, and the construction of this approximants is yeah, like there's some set of functions, and then he selects some sequence of functions.
In the end, his approximant is only going to be a single h anyway. So it doesn't even matter. But I think, but if you look at the paper, there should be a definition. But unless I completely, I don't know, miswrote it, I think it should be a sum. Okay, so anyway, so there's a tool that we need to do this, and this is theorem A from the paper. So this is by Stevenson. And so the link is on the seminar website. So we assume K is algebraically closed. Trivially valued. Or spherically complete. So there's also an or here, not an and. Spherically complete. Of residue characteristic 0. We let our subharmonic function. So by the way, sometimes I write E1, sometimes I write X, but this is the same. Huh? Okay, then the claim is for all Z in X, there exists a non-zero polynomial. So not just any function, but really a polynomial. Such that the limit okay, so that this estimate holds where this is defined to be the supremum X and E1 without the locus where this is minus infinity. Of the norm of X. sorry, this is a X. Yeah. So in some sense, so what this is saying here, we have a norm. This defines a norm on the set of all functions in. So we'll get to that later. So this is a norm on the set of functions where this value is finite, where the right-hand side is finite, right? So for every f, we get this value. Then you just modify. For some reason here you need this limit. I think this is sort of done by analogy in with a complex setting. I don't know. I'm not too sure, to be honest, about why exactly you need this, but apparently you do. And then the claim is that if you start from a z, so this is the input along with this function phi, then you can find an f, a polynomial, such that if you evaluate f in z, which is essentially what this does, and you twist a little bit by this phi, this is an upper bound for the norm of the polynomial you found under this norm. Now this looks like a sort of technical statement, and it is, I think. But, so you can work out, by the way, you can work this out in easy situations. For example, if you let z, if you take z to be anything, essentially, wait, I worked it out for something. I'm not gonna do it here, but I know if you let phi, for example, okay, I will just remark. I have to move this. Remark. If phi is alpha log absolute value of t minus a, right? So this is an example of a subharmonic function by what we saw before. Then if I did all my computations correctly, what we get is that this norm for any f, so I need to keep moving this to the supremum over 0 less equal to t less equal to 1 of the value of f on this disk. Right, so this a is this a times t1 minus like this. I think I did that correctly. So this is just an example to illustrate what kind of expression you get if you do this norm, right? And if you play a little bit with these sorts of examples, you can get a feeling for what this inequality is saying, I think. But for us, this is mainly just a tool to prove the actual statement. So just remember this, I'll get back to it in a bit. So the actual statement works similarly to in the, so by the way, I'll not give the proof of theorem A. I'll just note it because we will need it. The actual tool to construct this approximation of phi by something with analytic singularities is this de Maillet approximation. So we had a non-Archimedean version of that. Okay, so here the input is still this phi, this is fixed. Phi is input. Right, so out of that, we get I don't know how he calls this, but we get an ideal in K, so this will live in the end in K, curly bracket T.
I mean, this
and
is
it consists of
an
those
analog of multiply ideal of phi in non-Archimedean setting.
Is this what he calls it also? I don't remember this terminology. Okay, it does either way. This is just a set of points such that this expression here is finite, where this is defined as the limit epsilon going to 0 from above of the supremum. Okay. So here we see that we have sort of this expression that we had on the previous page too. And so we just restrict to all points where this is a finite number. And it turns out this is a principal ideal okay. So i.e. it's the ideal generated by some function g for some g. Okay. And then we fix m greater or equal 1. And then the mth, I think, mth, then that's 2 L's, I think, approximation of phi is phi m. So it's, again, phi is a function from x to, right, like before. So this is an m. And this is defined to be so you take all functions in which this norm evaluates to a finite number, and then you take the norm of f under your input x divided by the norm, sorry, there's a rubber in here, of f under this twisted norm. And then here you need to do an upper semi-continuity regularization. So this is something doesn't matter too much, I think, for now. Okay, so out of this, out of our phi now, we construct this new function. Okay, so let's make this. Okay, and then the proposition is that this is sort of what we want, proposition 4.6. This has analytic singularities. So in fact, the idea of the proof is to show that it is of the form beta plus log absolute value of this g, where this g is this g. right? So this is how you construct, this is how you show that it has these analytic singularities. Okay, so this is a good candidate then for the Desmahis for the approximation. And so then we get essentially to the end, because this is the theorem now that we are working towards. So under the assumptions, theorem B, theorem A, for all x in X, and m greater than or equal to 1, our initial subharmonic function is bounded, is a lower bound for the approximation. And if we add logarithm of the radius, then this gives an upper bound. Okay, so note just to be clear here, right? The logarithm, right? If this is 1, it goes like this. So this, because the minus sign is really a positive number.
Ah, it's a positive. Oh, okay.
Yeah. So yeah, this is negative, but this is minus. Okay, right? Because we are dealing with the disk of radius 1. Yeah. So I'll just briefly say something about the proof. So the upper bound is easy. Well, I mean this one. No, wait, the other one. Sorry, this one. And for the lower bound, you use this theorem, theorem A. Okay, so how do you apply it? Well, you define a small modification of your subharmonic function by subtracting the value that it takes on the Gauss point. Then this doesn't change this multiplier ideal. It's easy computation. And a norm also changes in a very easy way. And you just have the old norm times this value at the Gauss point. Like this. Okay, so you just modify the expression a little bit. And then, so for all z in X, there exists by theorem A an F in KT such that for all epsilon very small. So here you use a small variation of theorem A, but it's essentially the same statement. So this is X. Essentially, all you need to do now is just a computation. Once you have this function f, it's not long, so I'll just quickly write it down. And then the radius of x. Right, so this was the left-hand side here in theorem A, right? So we have this estimate here, and this is the left-hand side. And here you only, from theorem A, you only get the statement in this limit. But if you modify the proof, you can get it for all small epsilon. So you can fix small enough epsilon, and then the estimate works. So that's essentially what you do here. So it said this is less than equal to, right, this is the output of the theorem. This norm of f at this fixed point z that we fixed, e to the power minus m. So this implies, in particular, if you look at this for a little bit, well, actually, obviously, that f lies in this multiplier ideal. And if you just work out the definitions of these suprema and all that, it's not even, it's immediate by just rearranging this, this inequality. But this is equivalent with phi z. If you take, so now we apply logarithms and rearrange the sum a little bit again, is less equal to 1 over m log . Sorry, here this is in z. Right, and so this last equality is trivially true because this expression is the supremum over all expressions of this form. Right, so once you have this bound is obvious, and this bound you get essentially by definition from theorem A. And so then, I mean, that's the end of the proof essentially. So I didn't do the other bound, but you can look at the article if you're interested. It's really just writing out the definitions. This one you don't need anything difficult for, right? So the conclusion is that you get something very similar to this de Maillet approximation, where you start from an arbitrary subharmonic function, and you get these analytic singularities estimates that are bounded very tightly between the function and some error term.
So from the definition of phi m, it's not quite obvious that it has analytic singularities, right?
No, it's not quite obvious.
Can you tell in a couple of words what goes into the proof that it does?
So I think, if I remember correctly, you analyze this expression and you compare. So essentially, I think what you do is you compare this expression, or no, you bound this expression minus. I think it was something like, I'm not completely sure, but I think log of g divided by something like this. I think you analyze this expression, and then if you use the fact that you choose G to be a generator for this ideal, right? Any other thing over this supremum can be written as a multiple of this G. And then if you think about that for a little bit, I think once you are aware of the trick, it is not so difficult that this is bounded.
Okay, I see.
Right, so that you can essentially, after you change sort of the basis to G here, this supremum is essentially over, this is actually, you can rewrite it as the supremum over F in K T without 0 of log. Right, you can rewrite it like that because G is the generator. And if you think a little bit about this, then somehow you see that this is bounded. I don't remember the details, but. Okay, that's it essentially. So the conclusion is this Desmaillet approximation.
Okay, thanks.
Thanks. Thanks, Wim.
Thanks, Robin.
Yeah. So again, I'm not really, I didn't know too much about this topic before I started preparing this talk. So I don't know, if you want more details or a clearer story, there are these very good lecture notes on these Berkovich spaces that I found very helpful by Matthias Johnson. And that essentially is the main source. And then of course the article of Stevenson. Okay, that's it, I guess.
Yeah, that's it. So yeah, we have